Hello and welcome back to my Commodore 64 programming channel. In this video we're going to have a look at how to transfer a multi-load tape turbo loader game to disk. We're going to extract data files from tape, we're going to change the code to read from a disk instead of tape, and we'll create a new disk image. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. I'm going to go and use Gauntlet. So this is the Kix version of the Gauntlet 1 release on tape. I've looked at this version before in a previous video, but that was a technical deep dive into how the game actually worked. But in this video we're going to concentrate on the tape turbo loader and moving it to disk. So this is what the game looks like when you run it from tape. I was using the warp mode in Vice 64 debugger, or emulator rather, but this is ICU 64 with a relatively more recent version of Vice. So the tape version actually has quite a lot of multi-loaded files. It's like the disk version, so you can choose up to 2 players, and then it goes through and loads a whole bunch of stuff. Several different game files here we can see in the memory view that we have several different chunks being loaded. Of course, because it's the tape version, we have this rewind tape to start of side 2 message, which was quite a common way of dealing with multi-load games. So it would do all of its loading to begin with, and then all of the level customization data was sometimes put on side 2, sometimes it was asking you to reset the tape counter, and then every time you needed to go back to the first level again, you had to rewind to the tape counter. But on this game, it loads a chunk of data, and then if I use I'm using warp mode sometimes as well, just to make this quicker. Otherwise this video will get incredibly long. But I'm trying to get from level 1 to level 8 here. There's a little exit to level 8. There we go. So level 8 actually loads the next chunk of data. If I remember correctly, this game has 8 levels per chunk that's loaded in, roughly, I think. So if I played through levels 1 to 7 and then going into level 8, it would do this load. There are, if I remember rightly, quite a lot of levels, even on the tape version. There we go, this is what level 8 looks like. It's quite a complicated level. Let's consult the programmer's reference guide. We need to understand how the Commodore 64 uses the tape device, the C2N tape device. Let's have a look at the schematic. Didn't quite get the right page number there, so the page number in the PDF file doesn't quite match the page number in the contents or in the index. So there's the cassette connector on the right hand side there. We're looking for basically the one that's labeled D4, the CAS RD signal. The CAS RD signal then comes onto this page here, this one here. It then comes down, and if we scroll down a bit, and then CAS RD is labeled again, it goes into the flag pin, pin 24 on CIA1, which is a DC00. If we remind ourselves on how the CIA chips work, the Commodore 64 has 2 CIA chips, the complex interface adapter chips. These are like I/O chips with timers and all sorts of stuff like that. But basically, the flag pin on CIA1, which is a DC00, in that memory range anyway, the flag pin feeds into the flag buffer that then feeds into the int mask. I guess it's like a multiplexer, if you like, or the register perhaps. Oh yes, it has several different interrupts that you can create with the CIA, but the one that we're interested in is scrolling down a little bit here as it's documented. So the Commodore 64 is only able to read a negative edge sensitive input on the flag pin, which on CIA1 at DC00 is the negative edge from the tape unit. So the Commodore 64, even though it can write bits 0 and 1 to the tape device, the Commodore 64 can only read on a particular negative edge. So that means a transition of a signal just on the negative edge of that signal. So we cannot really read the positive edge on a stock Commodore 64. And when we want to read bits from the tape drive, when we're talking about turbo loaders, not all turbo loaders are like this, but a lot of turbo loaders use two different timings between these edges, these pulses, if you like, to signify a 0 or 1 bit. The standard kernel format actually has 3 different pulse lengths, but most turbo loaders only have 2. There are some turbo loaders that use more than 2 pulse lengths, but they tend to get a little bit complex quite quickly. And to be honest, you can write a turbo tape loader which is a lot faster than the default kernel routines and still just use 2 different pulse lengths. So we need to understand the tape turbo loader. We need to extract data files from the tape. We need to get data onto a disk. We need to change the code to read the data from the disk, change the game code. So we need to understand how the game starts booting its code, because it does have an auto run program right at the beginning of the tape, and of course that's loaded by the kernel loader, and then that does some, if I remember rightly, some decryption, some protection stuff, and not very much to be honest, and then it starts turbo loading data straight away, immediately after loading the kernel data anyway. So we've just set a ranged breakpoint from 100 to 1000 in hex, and there we go. We've got our main auto run entry point, which is at 3300. We'll just step through this until we get to where the turbo loader is initialized and it wants to start loading the first block of turbo data, because we need to understand how the turbo loader works. There are different variations on how a turbo loader can work. There's not just one way of writing a turbo loader. There are lots of different ways of implementing a tape turbo loader, as there are on the disk device as well. But we're just going to keep on stepping through this code, understanding what the code does. So that's a funny thing, is that FCB7 on the kernel here anyway immediately goes to an RTS. So actually that code which tries to JSR to FCB7 just hits an RTS and comes back again. Maybe that's a kernel revision check, or maybe it's checking for a modified kernel and hopefully it would error out at that point, or just crash, perhaps. Anyway, so we just keep on stepping through this code to see what it does. I can see there that it's initializing 328 and 329 with, in hex, it's 210. That's in low byte, high byte format there, so we swap them around, so it's high byte, low byte when we're reading the address. And that vector is, of course, the kernel stop routine. That's basically trying to trap out the kernel stop routine so that we can't press stop to interrupt the kernel load. But it's already loaded a chunk of data, so I don't know why we're really claiming that. Don't really need to, because it's going to jump into the tape turbo load code quite quickly. There's an EOR there with 300 Y. There seems to be doing quite a bunch of decryption of the data that's been loaded. There's more decryption and then a little bit of data moving around. Well, just data decryption at this stage. I'm setting up some breakpoints to just after the decryption code runs. Okay, that's just more some slight Vic setup code there, I think. And then we get into this code here, 611. This looks like a good starting entry point, doesn't it? Where the loaded code is decrypted. We've got the boot code there appearing in the text screen debug view in ICU64 there. We can see the file name boot code. It looks like that's the next file name that's going to get loaded. But we'll remember 611 in hex as this useful entry point, because all of the code has been decrypted. So I think that we can start modifying or potentially modifying this code so that instead of using a tape turbo loader, we can modify it so that it uses the disk kernel loading stuff instead. It seems to be wanting to reinitialize vectors and stuff like that, which is useful. It's also going to FFBD. FFBD is set file name parameters. It's interesting that this variant of the tape turbo loader code, or the tape loader code, is actually using the kernel setup routines. It's reusing some of the standard kernel zero-page memory locations for things like file name. If we have a look at the memory at 647, there's the boot code file name, and that's what we could see in the debug graphics map text screen view there in the top right hand screen. This is interesting. It's setting up or claiming the vector for the kernel load routine. So even if the game tries to call kernel load, it's going to be redirecting to the code at 914 in hex. So we'll step over that. It's doing FFD5 now, JSR to FFD5. FFD5, if you remember your kernel routines, FFD5 is load RAM from device. If we step through this disassembly, then very quickly it jumps indirected through the vector at 330, which is the vector that was just claimed to run the code which is inside this auto run code that's just been loaded from tape. This claimed load vector, which is our just loaded code, JSRs to 900 in hex. This looks like the start of the tape turbo loader setup code. This just basically reinitializes the IO, I think, if it's FF84, which is inside the kernel. Let's just, yep, there we go. Initialize IO devices, that's FF84. That initializes CIO1, CIO2, stops the interrupts and stuff like that, if I remember rightly. And here we are. I think this twiddling here of 01 basically starts the tape motor again, I think, if I remember rightly. This is stacking the current values of 1, which is the processor port, and also D020, which is the VIC screen border. Oh look, so it's loading from BB indirected, so BB and BC will contain a memory address, and that memory address is the file name, of course, which contains boot code. It looks like it's taking, it's using B7, which is the length of the file name as well, which is where the standard kernel routine stores that into B7, which is, you know, like the default standard version of the zero-page memory location. And it looks like this code is just filling the rest of the file name up to a maximum of 16 bytes with the space character. So it then goes into this code at 87D, which also initializes some zero-page memory locations. So it's initializing FE02, F9, and B7 with 0. And then look, it's setting the interrupt flag, so it's disabling the interrupts. Aha, there we go. Okay, so this tape turbo loader is using the DC04 and DC05 registers in CIA1, which are the first timer. It's setting up an interrupt source, and that interrupt source is using 90. So DC04 and DC05 is CIA timer A, timer 1, the first timer. DC0D on the interrupt source is basically setting up an interrupt to occur on the flag pin changing. the signal level of the flag pin. So enable interrupts generated by, my comment there is the positive edge on the flag pin. It's probably actually in the negative edge, right? But that doesn't really matter. It only counts one edge. It doesn't really matter what edge it is, to be honest. The Commodore 64 is executing this correctly, even if the comment in the standard library is not entirely correct. It's just an edge. Anyway, so what this means is that the interrupt is configured to generate an IRQ, and then that IRQ will jump into the kernel vector at FFFE and FFFF. There's some code here at 8A6 which looks like it's testing 02, and in a very tight loop, and then it looks like it's comparing FE in 0 page with FF. This does look like the end of load detection. So the kernel, the tape turbo loader IRQ will probably be hitting the flag at 02 in 0 page to indicate that the file has completed loading, and then it's just doing a comparison with the FE and FF. That's almost certainly a checksum comparison. So here we go. This is an IRQ that's coming in now. You can tell because it's doing the interrupt flag is active in the program status register, so it's set, so that means we're hopefully inside an IRQ, and also it's doing a PHA, TYA, PHA, which is kind of like a standard interrupt. So anyway, there are several ways of measuring the time between pulses coming from tape, especially when you're talking about tape turbo loaders. You can use a timer, and I'm going to be putting these notes into the debugging text file as always and committing it to source control, GitHub. Anyway, so you can use a timer that counts down and stops, and then you can detect if the timer has stopped. You can use a timer, but you can shift the low or high value of a timer to get a bit out corresponding to if it's a short length or a long length, and then you can use that bit and you can shift it into your byte that you're trying to decode coming from tape. You're always, generally speaking, talking about trying to get reliable bits from the tape. Okay, so there's another way. So you can, for example, use precisely timed sequences of opcodes to try and time the differences between incoming tape pulses or edges from the tape unit. But usually with a tape turbo loader, a short pulse is usually, but not always, 0, and a longer pulse. And your longer pulse usually is twice the length of a short pulse, is corresponding to a bit 1. In this code, it's loading accumulator with DC05, which is the high byte of the timer, and then it's EORing it with 2, and then logical shifting it right by 2 to the right, which gets that bit into the carry, and then it's shifting it back out again. You see, what you could use is that you could use the, so it restarts the timer. So once an edge comes from the tape unit, we're telling it to restart the timer by updating it in DC0E, of course, because you want to restart the timer once you receive an edge from the tape. But if you use the timer in one-shot mode and then you detect whether or not that timer has completed, then that's a little bit more accurate than doing this shift thing with the low or high value of the timer. But in this tape turbo loader, it's shifting the high byte from the timer out and trying to get the timer values that way. So all it's doing is that it's using this value in FE, it's using the FE value in A9 to represent a string of binary digits with you can do it either way. You can either have all zeros and then a 1, or you can have all 1 and then a 0. But basically you're either looking for a clear carry or you're looking for a set carry to be shifted out from the left-hand side, from the most significant bit, while you are shifting in the bits that you're reading from the tape. So the last bit that you shift in here, as you can see, we're gradually shifting, and then the last bit is either a forced 1 or a forced 0. So when carry, in this case, carry equals 0, then we know that we've shifted in 8 bits. It means that we don't need to have a separate register to count the number of bits. We're just relying on the carry being appropriately set or clear depending on the number of bits that have been read from the tape. So this is quite a standard way of writing a tape turbo loader. It's quite efficient because you don't need an extra register to count the number of bits or anything like that. You don't need to have a separate 0-page memory location. You just shift around 8 bits, which is quite a cool way of doing it. Reusing the same register, reusing the same 0-page memory location to maintain a dual purpose. The byte that you're reading from the tape, and also to make sure that you shift out or shift in the relevant correct number of bits to make up a full byte. Once the full byte has been received, it looks like it hits this jump. So there we go. We've currently read in a 0 value from the tape. And then once it hits that jump, it then goes into this sequence of compares. So it looks like it's comparing with 20 in hex. It looks like it's then self-modifying the state machine code. So we need to understand the tape turbo loader from the point of view of several different things. We need to know, for example, the sync byte that the turbo loader code expects. We need to know the file name. We need to know the start address. We need to know if there's an end address or a size of data. We need to know when the data starts loading, and we probably need to know where there's a checksum. The checksum is sometimes in the tape header before the data. Sometimes the checksum is after all of the data. We're not quite sure yet. We're not quite sure about the tape format. But to be able to extract the files from the tape, we need to understand the low-level turbo file format as it's stored on the tape. Now, lots of different tape turbo loaders have different tape turbo loader data format on the tape. So it really is beyond the scope of this video to try and understand all of the formats of the tape turbo loader data formats, but we'll just be concentrating on the format that's used in Gauntlet, in this particular version of Gauntlet as well. We'll just try and go through the process of understanding this loader, because once we learn how to do it here, then this learning is very transferable to other tape turbo loaders as well. So that's what we hope anyway. But yeah, it's generally true. I mean, tape turbo loaders are kind of similar. So we'll put a breakpoint later on in this stack of compares, so that once we start reading data, there we go, there was quite a lot of blank space on the tape before it actually started getting data. So here we go. We've read what looks like the first 2-0 sync or maybe pre-sync pulse. It then self-modifies the jump at 94C by updating 94D. So that's updating the low address of the jump. So the state machine is being changed. So once it's read 20, the state machine then changes to making sure that we have 20, or make it looks like it's comparing it with FF as well at 969. Look, so that's something we need to be aware of. First of all, the tape turbo loader will shift a value until it gets a known value, and then it tries to synchronize to that known value, because then it will try and synchronize that known value before it then starts trying to read real bytes. And that's because when you start reading pulses from the tape unit, you don't know if you're in the middle of reading a byte, or in the first couple of bits of reading a byte, or if you're in the last few bits of the current byte on the tape, because the tape can be forward wound and rewound, and you could miss a byte, or if the tape has been written badly at the beginning, you might be missing some bytes, or bits rather. So you need to make sure that the bytes you're reading are synchronized with the data that you kind of expect. So that's why you have these known patterns at the beginning, so that your code can synchronize and lock on to the bits that you're reading from the tape. Once you start reading expected bytes, then you can assume that you're hopefully not going to lose any bits going forward. You can add some error correction and stuff like that in there, but generally you don't need to with the tape turbo loader. An XOR check is usually sufficient. We need to know the speed of the pulses in the tape as well. Now we can read that speed from, or we can try and deduce that speed from the timer value, but we can also have a look at the tape file to deduce that speed much better later on. So once we read FF, and we've got FF there in the accumulator in the register view, that seems like it's signifying that there is a start FF before a tape header, perhaps, because look, the next part of the state machine is loading Y with B7. B7 is then comparing it with 293. So it's reading, it's the tape loader then gets the accumulator next byte after the FF, and then it starts to compare with 293 and 293. So the byte after FF is 42, and then it's comparing it with what's it 293, and that's the file name. So then this state machine checks byte after byte up to 16 bytes, 10 in hex. It checks that the bytes arriving from the tape correspond to the bytes that we want for the file name. So this way of writing the tape turbo loader code as a state machine is pretty common. And that's because you have an interrupt, which in this case, the interrupt is decoding full bytes from the tape now. And so you need to remember what state you're in so that you can then process the next bytes in the stream. So writing it as a state machine with self-modifying code, which self-modifies a branch or a jump to then go into this different state depending on the bytes that you're reading and where you are in terms of the sequence or the stream of data coming from the tape at this stage, the stream of bytes, then you're going to be populating different data. So after the file name check has succeeded, look, it's starting or wanting to start to store into FA, for example. This is setting up, it's setting up the next values to read. So this is the next part of the state machine. So it's storing the accumulator in FA. The accumulator is, well, after the file name, it looks like there's a 0 byte coming, and then it's storing it into FA. If we have a look down through the code later on, it looks like it's reading 4 bytes into FA, FB, FC, and FD. And then it compares it with FE, and then if it's FE, it then looks like it resets the state machine back to start to read from FA again. But look, there's an indirected store FA bracket comma Y. So it definitely looks like, oh, there's an EOR as well with FE and then store back into FE. So FE looks like it's going to be the calculated rolling XOR value, the checksum that's coming in. And it looks like it's comparing FA and FB with FC and FD. So it looks like FC and FD that's read in, or will be read in, because it hasn't started reading them all in yet. From the way that state machine's executing, yep, okay. We're just stepping through each complete byte now. And, yeah, okay, so another complete byte. So here in the state machine execution, we're just about to write a byte into FA, indirected comma Y, and there's the 4 values at FB, FC, FD, and FE, and that's in low byte, high byte format. So we swap them around, and that means that we've got a start address of 2000 in hex and an end address of 3B00 in hex. So it looks like we're building up our understanding of this particular format of tape turbo loader data. So it looks like we have an FF byte to signify the tape header start, and then we have 16 bytes of the file name. We have 4 bytes for low and high start and end. looks like we've got the data appearing after that. There's a great big stream of bytes. And then after the data store has finished, we'll put a breakpoint on the next part of the state machine. So it's loading a whole ton of data into memory. We can see that in the debug memory view. We'll let this progress and then hit the next breakpoint in the tape turbo loader state machine, which looks like it's storing the accumulator. It will do. That's the last byte that's read in for the memory store for the loaded data. So we'll put a breakpoint back into the state machine's jump after it's just loaded the next byte. There we go. This is the next byte coming in. So 25 then goes into FF. And look, it increments 02 in hex in the 0 page memory location. And then it tries to restart, reinitialize the state machine and basically loops around and starts the next IRQ. But look, the main line then comes in after the IRQ returns from interrupt, and then the main line check for 02, which is the load complete and checksum check. So it's checking FE and FF for equivalence. And then it jumps to 9EA to indicate that the load has finished. So let's update the debugging notes text file. So checksum, we have 1 byte following the data, and that is for the size, which is obviously end address minus start address. We need to know the speed of the data in the tape file so that we can try and decode this using a tool rather than running the tape turbo loader code or trying to intercept all of the possible files that are loaded by the game. Okay, so if we have a look at the tap file, we can see on side 2 as well. So we start with turbo data. We don't have any kernel data at the beginning. So we just look here, and inside the tap file, we can see that we've got 20 in hex and 41 in hex. So if we have a look at the hex value, multiply that by 8, which converts it to cycles. And that's because the tap file reduces the resolution of the pulses by 8 cycles. That means that we have 2 pulse lengths. We have 100 and basically 200 in hex. So we know the speed of the pulses, the timing of the pulses. So a 0 bit, in other words, clear carry, corresponds to the short pulse, which is 100 in hex roughly, and a long pulse is 200 in hex, and that's going to be a 1 bit or a set carry when we were looking at the tape turbo loader code. So I can use my tape tool to read kernel encoded bytes and also turbo encoded bytes. So this tape tool has a few configuration values. We've got 0 bytes for the tape header, we've got 100 and 200 for the tape turbo speed. We're looking for a sync value of FF, which is the start of the tape turbo header, and we've got the endianness as well. We can set whether or not it's little or big endian bits in terms of bytes. We can verify that we can read byte values from side 2 of the tape, for example. We can see here that we've got 16 bytes for the file name, then we've got 4 bytes for the low and high start address, and we've got data following. And this looks like kind of expected data. We can see from the tap file that we've got 8 long pulses, and that corresponds to the 8 1 bits that make up FF in terms of a byte, because don't forget that a byte is 8 bits in Commodore 64, 8-bit land anyway. So we can use the tape tool to extract the tape header, tape information from the files. So we can set up the 16 expected bytes for the file name, the start address, the end address, which are 2 bytes each, the data following, and then the checksum expectations. We can use the tape tool to set up those values, and then we can read the stream of the turbo tape encoded data using this methodology. So this is the file name byte range, so 0 to 15 is are the bytes used for the file name, and then the start address is using offset 16 and 17, and then the end address is using offset 18 and 19. The file data starts from byte offset 20, and then the XOR starts from byte offset 0 after the data has completed loading in. And then we've got the file header, size, and everything else that we're using for the configuration. The tape turbo speed, the endianness, and then the sync marker. And there we go. We can see that on side 2 we're reading auto text, comma S, comma R. We've got A1 files. We've got lots of A1 files. There was also an A file there at the beginning. So the file name was A, and then on this tape, on side 2, all of the following level files after the initial level file are called A1. On side 1, we have turbo encoded boot code, gaunt.spr, spicf gauntlet, data title 244, gaunt font, $7000, for example. If we have a look at the directory where these files have been dumped, I basically prefix the file names with the index from their original position in the tape file, and that's just to avoid the situation of overwriting any duplicate file names like the A1 file. We don't want to keep on overwriting that. We want to maintain all of the individual files that we read from the tape. So anyway, once we have these files, what we can do is that we can try loading them. So we tried loading the Gauntlet file, and that was those were the sprites in memory. Let's load spicf gauntlet, and then we'll use ICU64, the graphics map debug view. We'll look for a bitmap in memory, and there's the Gauntlet bitmap data that we loaded. So we're pretty much sure that the data that has been extracted from the tape turbo data format on the Gauntlet tape, side 1 and side 2, we're pretty much sure that that data is good because it looked good in the debug view there in ICU64. So we need to change the game code now, so that instead of using the tape turbo loader, we want to load these files from disk. So this is where we need to start hacking around the initial auto run code, because the initial auto run code loads the tape turbo loader code and everything else like that, right? And does all of that setup code, which we need to also try and keep. So we need to start understanding that code. So I think we can go back to 611 in hex, right? Which was that entry point that we noted down last time as a good entry point start. So let's put a breakpoint at 611, and then let's load again from tape Gauntlet at the beginning, and then it does all of that decryption, or well, you know, it goes through all of those EORs, right, which is effectively decryption. And now we need to start putting in our code into 611. We don't really care about the load accumulator with DE00. I think that's probably just trying to check that it was probably trying to check for a hacker cartridge by reading the IO space there for sometimes like a hacker cartridge is there, but it looks like that it's been no-opt out the code after it. So we'll just put our code here. So I think when we start running, we want to initialize the processor port to enable the kernel and IO. So that's what we'll do. We'll put the 3.6 in hex into 0.1, which is the processor port. I think also we should probably just really make sure that we're reading from device 8, because we'll be using the kernel load functions. So what is the device number? Yeah, that's definitely the kernel with IO, just making sure that the 6 on the end going into the 0 page processor port register is correct. But yeah, I think we need to really make sure that we're reading from device 8, which is the disk device, because we'll be using the kernel load routine. At least at this stage, just keeping it simple. We're not going to try and implement an IRQ disk turbo loader. We're not going to try and implement decompression or anything like that. We'll just be loading the file using the kernel load routine. So we'll store that into BA, which is the current device number. So there we go. We've put our code there at the beginning. And then I don't really care about the clearing of the color memory that it was doing. But anyway, the next piece of code, we need to start overwriting from 917. So I think we'll keep the JSR to 900 at 914 because that initializes the IO and CIA1 and CIA2, I think it does. Anyway, so we'll just overwrite the tape turbo load setup code now to restore again device 8 and putting it into BA. Then we will load accumulator with 0 and then JSR to F4A5, which is inside the kernel load routine. We don't want to go through the vector or anything like that, but we need to make sure that the accumulator is 0 because, as you can see, it stores the accumulator into 9.3 in hex. And 9.3, if I remember rightly, that's the load or verify flag. And we want to make sure that we're loading data, not verifying data, because verify doesn't load, it just verifies. So anyway, after that, I think we'll duplicate what the tape turbo load code does and then basically reinitialize the interrupt control registers for CIA1 and CIA2 just to basically turn off all of the interrupt sources. Okay, we don't want any spurious interrupts to occur as we're switching back to the game code, I think, so we'll just turn off the CIA1, CIA2 interrupt sources. We'll also turn off the VIC chip interrupt sources. We'll disable all of those interrupts as well, just to be really, really sure. That is the VIC2 interrupt control. There we go, D01A. We'll just put 0 in there. And then after that, I think we're pretty much good. We just need to RTS, of course. We need to return from the subroutine. So that's what our code now looks like. Initializes IO, initializes the disk device, does the kernel load by jumping into the kernel load routine, and reinitializes again, or resets the interrupt sources that we know about, and then that should be it. So we'll save that as a Gauntlet boot, and we'll put the start address at 611.prg. We'll save that memory range from 200 to whatever it is, 930, right? 930 is just after our code that we've added, but it's not really saving out the tape turbo load code because we don't need to save out the tape turbo load code anymore. And that's just basically the memory range that we're interested in, I think. 200 all the way up through the extended 0 page includes all of the vector state as it is right now, so we'll just keep that as well because it's useful to have. So we don't, I think the code also resets the vectors, yeah, it resets the extended 0 page vectors anyway, but we'll just, keep it just for completeness sake. It's probably more data than we need, almost certainly more data than we need, but it's kind of like a complete chunk, so we might as well just keep it. If we wanted to optimize it later on, of course we could, but I don't think we'll spend too much time, overthinking and over-optimizing this. This is meant to be a quick video, not a great big long video. Anyway, so then we use my compression tool. I use my compression tool because I know that it works and it doesn't have all of the problems of other compression tools that corrupt 0 page and stuff like that. So anyway, I'll be using the -64 MBU mode, which is basically an auto, well, it's a sys command at the beginning and it's an auto extracting, self-running thing, self-running program file. We'll put that at the beginning of the disk image. Okay, C temp gauntlet boot. So if we run that, C temp gauntlet boot.prg, we can see if we run it, and we'll put we should really put a breakpoint at 611. Where's that file? Let's just dump it on there. And then you can see what it does. It loads, it decompresses, and then it jumps into 611, and then it starts running our code. Now, of course, that was just dumping the program file onto the emulator. What we need to do is that we need to make sure that it's in a disk image, because this only really makes sense when we have those files in a disk image, right? So yeah, you could see that it did a very quick decompression, and then it restored the state of the memory that we want. It's got all of the boot code stuff and everything like that. And I'm pretty sure that that's working really well, but we need to put it in the disk image now. So we need to get those files that were extracted from the tape. We need to construct the disk image in a way that we know is expected to work, right? So we can see here that it's starting to go into the kernel code, but we don't need to run it right now as a PRG file. We need to run it as a disk image. So let's get the D64 editor out. Where is my D64 editor? It should be here somewhere. There it is. Okay, let's create a blank D64. That's fine. We'll just save it. See, we'll call it my Gauntlet.d64. That's all good. Okay. Now we need to start plonking in the files. I could, of course, use like a tool like C1541 and then create a batch file to do all of this too, but this is just a quick hacky test to see if everything works. It would be better to make it a reproducible, like a batch file or a make file or something, but I can't be bothered right now. Anyway, so we'll just put in the Gauntlet boot, and then we need to copy in all of these files that we extracted from the tape, right? So I'm trying to put them in roughly the right order, but yeah. Oh, look, we've got two files with identical names there, apart from the prefix of 15 and 16. I think those two files are identical. They were both extracted from side one of the tape. Let's just do a check. Oh, okay, yeah, the compare tool says that they are binary the same, so we're not going to include both on the disk. We need to edit the file names so that they match the file names that were extracted from the tape, minus all of the spaces at the end of the file name, because the game sets the correct file name in the file name setup kernel call. So we'll just make sure that these are all spelt correctly and that the last few characters of the file name are correct. Technically speaking, I should have probably put the file index as a suffix rather than the prefix, and then I wouldn't have to edit them so much and restore the missing characters at the end of the file name. But hey ho, there we go. Never mind. I might alter my tool to do that. But I really wanted to maintain their file ordering as well, in terms of sorting it by file name. But it's pros and cons, right? Swings and roundabouts. Anyway, glove.bin. Okay. Anyway, Gaunt prog, $8000, Gaunt CHR 4800. I think these file names, they seem very similar to the file names that were in the official disk release, right? I'm not entirely sure. I did look at the disk release of Gauntlet. Anyway, editing these by hand is hopefully one-time effort. Hopefully I'm not going to spend too much extra time in this video creating this disk image using the D64 editor, but I do like D64 editor. It's good if you want a nice GUI interface to creating a disk image. So now we need the A file, which is the first 8 levels, which contains the first 8 levels, right? Levels 1, 2, 3, 4, 5, 6, 7. Is it? Yes. And then this contains level 8 onwards or something like that, if I remember right. The A1 file. There we go. It might be level. Yeah, because yeah. Okay. So we might put in the next A2. We'll call this A2. Just to maintain the sequence. I don't know if we'll get to loading, like level 16 or 17 or whatever it is, but we'll see. I'm not going to put in the rest of the level files. We'll just put in 3 level files to begin with. We need to save that. Once we save it, then in theory, we'll leave that open. In theory, let's get the disk, the D64. Let's get that D64, and then let's see if we can run it. Plonk it in there. There we go. Don't know if I missed it or something before. But there we go. Okay. Wrong file maybe. Anyway, so there we go. The breakpoint at 611 has hit. Yeah, I don't really care about the clearing of the color RAM. What I care about is whether or not the kernel load routine loads data. I'm trying to step out using the machine code monitor. I'm trying to step out from the kernel load routine. It's the thing with the kernel load routine. It really messes with the stack sometimes, and it's sometimes not able to step out cleanly. There we go. We'll put the breakpoint after the kernel load. We'll just exit now. Okay. Well, it seems to be loading some data. I can see that in the memory debug view there in ICU64. I can see the track and sector information displayed in the emulator is ticking down. It track 17 to track 16. It doesn't really display the sector information, right? That's the device number and then track and sector. Yeah. Anyway, so then it's completed and then it's running our or gonna run our code for disabling CIA1 and CIA2 interrupt sources, and then also disabling the VIC interrupt source. There's 0, 0, and 2, 0, and then it's got a 4C. Okay, so let's disassemble the code, and there we go. That's great. What's disassembled there matches the hex bytes that were in the expected boot code file, which is the file that was extracted from tape. So I think that's worked. We'll just let that continue running. Oh my word, it's loaded the next file or two as well. Okay, great. Let's just continue on, shall we? There we go, loading the next chunk of data. We can see that in the memory debug view. And in theory, fingers crossed, toes crossed, everything crossed. It's still loading in the background. It's loading a lot of data. Don't forget that there's quite a large bitmap being loaded. That's the next breakpoint for the next file that's loaded. Let's just remove that. I think we can safely say that it's successfully loading data, right? We'll just remove the breakpoint, I think. Let's let it continue on. It's loading data, loading another chunk of data somewhere else in memory. There we go. Wow! Well, it loaded the title screen with the color bar Gauntlet logo, which I think was sprites, right? Expanded sprites. It works to this stage. Let's see if it works for the next part of the game, right? So there we go. Okay, that's good. Press space, and again, there we go. Okay, it's now loading the next chunk of data. Wow, this is working better than expected. Okay, cool. Things don't usually go this smoothly the first time you try them. Sometimes you'll have false starts, and sometimes you'll notice that there are crashes, and that's sometimes because you are assuming state, or maybe the kernel's not enabled and you can't call the kernel load routine. But this game was calling other kernel routines just before doing the load, right? So we could pretty much safely say that the kernel was at least enabled. But it's good that the 0 page is restored to a certain extent, that all of the vectors are still there and working and everything. So there we go. We've chosen the character. It's now probably loading character data. Let's just warp through that a little bit. I can see quite a lot of code running there in the memory events view. The blue bottom right hand corner there, the blue pixels indicate execution of code, and that's in kernel space, not in RAM, which is on the left hand half of the memory events view there. On the right hand side is, kernel space and everything like that. So this is just loading a whole chunk of data now, and it's loading another chunk of data now, much lower down in memory, near the beginning. So it's loading more chunks of data, copying data around. We've got the rewind tape to start of side 2 message. We'll just delete all the breakpoints there. I want to make sure that I understand how the game starts loading different level file names. So I'm putting a range breakpoint there. So to see how the game calls into the load routine, let's set up the graphics map debug view there so that we're looking at the beginning of memory again. Okay, that's all of the start of memory that we extracted last time. That's good. Let's press fire. Okay, so the game, when it starts loading level data, it jumps, or JSRs rather, into 850 in hex from 98B8. Okay, the accumulator is 1. Okay, so it looks like 98B1 changes the accumulator between 1 and 2, and then JSRs into 850. This is kind of expected because the game turbo tape loader code had lots of repeated files, one after each other, called A1. So I'm guessing that the first pass around, the game code tries to load a file name with length 1 and the file name is stored at 85A. In this case, it's A and then 1, but because it's only 1 byte long, it only loads A. And that's the first pass through. So it loads the file A from tape and also, hopefully from disk. But the second pass around, the game code seems to call this code. I'm just checking to make sure if there's any previous code there. Okay, so there is. It's just a JSR, the JSR, and then another JSR to 850. Okay, so 82C9. Okay, so it looks like then the next iteration of the game code then loads the accumulator with 2 to say basically use 2 bytes for the file name, and then that loads the file A1. Okay, so this code at 850 will, in the tape version, it will try and repeatedly load file A1. The A and then A1 and then A1 and then A1 and then A1. And that's because you could have duplicate names on the tape. But on the disk version, I think, as I just wrote there, I think we need to modify this code if we're going to produce a proper version. And I don't think we're going to have time in this video, but if we wanted a proper version, then the code at 850 will need to spot this sequential repeated attempts to load file A1 and then redirect to file A2, file A3, file A4, file A5, and so on and so forth. Okay, but we're not going to, I don't think we'll have time in this video to actually put in, file A2, file A3 into the disk. But yeah, here's level 1. Let's get the key. Let's try and fight all the way through here again, and then go to level 8. So we can see at this breakpoint that the accumulator is 2 and the memory address for the file name points to A1. Okay, so now we're trying to load 2 bytes, and that's because it's the next level chunk. So that's definitely confirmed that that's how the game works. So let's let that second chunk of level data now load. Then we go to level 8. And then there we are, there's level 8. So yeah, I think that's going to be kind of like a successful transfer of the Gauntlet tape version to disk to use the standard kernel disk loader. Hopefully that was a useful quick run through on how to understand tape turbo loaders, how to understand tape turbo loader data formats, and then extract and then transfer multi-load tape games to disk relatively intact. I tend to like to make the fewest amount of original code changes as possible. I like to try and keep as much original code existing in the release. So, you know, I didn't really want to spend too much time and effort in removing all of the rewind tape messages or press space or press play on tape and stuff like that. I just wanted to keep it as original as possible, but that can be left as an exercise for the viewer, if you like, to try and polish up all of that. So thank you very much for watching these Commodore 64 coding videos. If you like these kind of retro Commodore 64 technical deep dive coding type videos, then please do consider liking or subscribing to my channel, and I really hope to catch you around next time. Have a great day, evening or night, wherever you are.